Okay, good evening, everybody. So what we're going to do is we're going to kind of go through how um, each one of the problems on the final review needs to be set up. I'm not actually going to solve it necessarily. Some of them I might, some of them I might not. But I just want to give you an idea of how they get set up. Okay. So, first one, 11 gram mass is moving to the right at 8 meters per second. The second 7 kilogram mass is moving to the left at 6 meters per second. The two objects stick together after they collide to determine the change in momentum of both masses. Okay. So you really do want to pay attention to this one. The important thing here is understanding that momentum is conserved in both elastic and inelastic collisions, right? So both of the equations that we have for momentum so that's elastic collisions, right? Things that bounce off each other. We start with two objects, we end with two objects. And then we have inelastic collisions, which look like this. So it starts off looking exactly the same. We have the momentum of both objects, but then we end up with only one object. So we need to add their masses together, and there's only one velocity. So as we're looking at this, the important thing, what I'm trying to point out, is that they're both equals, right? They're both equations. Meaning that momentum at the beginning and the momentum at the end is equal, thus conserved. Okay, so mass A here is 11. I'm not sure why that just switched to a significantly bolder one, but that's fine. Mass A is 11 kilograms. Mass B is 7 kilograms. The velocity of A at the beginning is 8 meters per second. No, it's not writing at all. Okay, that's fun. So 8 meters per second, and V sub B sub I is 6 meters per second. So we look through, it says the two objects stick together, and what we're looking for is the change in momentum of each object. So what we're going to do is we're going to find the final velocity first and foremost. So because they stick together, it's an inelastic collision. So that's the equation that we're going to use. So we're going to go 11 kilograms times 8 meters per second plus 7 kilograms times 6 meters per second equals 11 kilograms plus 7 kilograms times our final velocity. Because remember, all of this momentum, P equals mass times velocity. So this is going to give us 88 kilograms per millimeters per second. That's how much velocity the large ball has at the beginning of the problem. Now, I notice I did something wrong here. One's moving to the right, one's moving to the left. So this one's going to have a positive 8 meters per second. This one's going to be moving negative 6 meters per second. So this is going to be negative 42 kilogram meters per second. And we add them together. 11 plus 7 is 18 kilogram meters per second times V sub F. 88 minus 42 is 46 kilogram meters per second. That number is important because that's the total amount of momentum at the beginning of the problem. Equals 18 kilogram meters per second. Sorry, just kilograms. Times final velocity. So we divide by 18 kilograms. to see how fast the final combined object's going to be going. And I believe it's like 9.6. That's not right. Let's go 46 divided by, I'm thinking of a different problem. 46 divided by 18 is 2.6. Okay, so let's go. We only have one sig fig here because of 8 and 7. So we're going to go 3 meters per second because we have 2.555. Okay, so we have 3 meters per second equals our final velocity. So that means that our large ball, or mass, the 11 kilogram mass, now has 33 kilogram meters per second. We know that the change in momentum equals final momentum minus initial momentum. So we're going to go 33 minus 88, and we get 55 kilogram meters per second. Okay, so the 11 kilogram mass lost 55. It's negative 55. The other one, we're going to go 7 kilograms times 3 meters per second. That's going to give us 21 kilogram meters per second. We're then going to go 21 minus a minus 42, and that gives us, this is 42, right? 63 plus 63 kilogram meters per second. Again, we only get one sig fig here, so this is actually going to equal 60 kilogram meters per second, and this is going to equal 60 kilogram meters per second. So notice what we have here. We have one losing 60 kilogram meters per second, the other one gaining 60 kilogram meters per second. And that should fundamentally make sense. If momentum is conserved, then however much one object lost, the other one's got to pick up, right? If one loses more than the other, then we've lost momentum, and that's not happening. Okay. So that's how the first one goes. Angie has a mass of 85 kilograms and is in space next to a satellite with a mass of 800 kilograms. She pushed herself away at a rate of 1.8 meters per second. What is the velocity of the satellite? So here, straight up conservation of momentum problem, right? We look at the momentum we have at the beginning. And it's got to equal the momentum we have at the end. Now the tricky part here truly is just keeping track of all of your variables. So here, mass of A, let's call that Angie, that's 85 kilograms. Mass of the satellite, we'll call that M sub B, that's going to be 800 kilograms. Now, they start off not moving, right? So V sub A sub I equals 0 meters per second. V sub B sub I equals 0 meters per second. And we know that at the end of the problem, Angie's moving away. So let's call that negative 1.8. Sorry, weird little 1.8 meters per second. And we're looking for V sub B sub F. So what we're going to do, we know that because they start off with both 0, that's just going to equal 0 kilogram meters per second. We know that Angie's mass isn't changing, so we have 85 kilograms times negative 1.8 meters per second plus the 800 kilograms of that times V sub F. Now this is going to make a really small number. Which should make sense, right? The satellite's about 10 times bigger than Angie is, so its velocity should be roughly 1/10 of what Angie's is. So you should end up with something less than 1, like significantly less than 1. What you're going to do is you're going to do your algebra here, multiply 85 times negative 1.8, add that product to both sides, divide by 800, and you're good to go. What is the difference in gravitational force between two 10 kilogram masses when they are 1 meter apart and when they are 5 meters apart? Well, when we look at the force of gravity, we're going to look at newtons. Universal law of gravitation. There it is. Force of gravity equals G, which is 6.63673 e to the negative 11th. So we're going to have two scenarios here, right? One where we're dividing everything by 1 squared, and one where we're dividing everything by 5 squared. Now that's the only thing that's changing, and yes, that is in fact a 5, even though it looks like an 8 or an S. Okay, and again, the pen's being silly, so that's fun. I forgot my decent pens at the school, so I'm using one of the older ones I have at home. And it is going swimmingly. Okay, so if I go here, so this will be a little weird, but it should be okay. So notice that over here I have one. Oh, I'm in erase. I don't want to be in erase. So I have 1 squared, and over here I have 5 squared. So the rest is going to be the same, right? G is still going to be 6.673 times 10 to the negative 11th, and both masses are 10, so we're still going to have times 10 squared. But one of them is divided by negative 1 squared, the other one is 5 squared. Now, we know that gravitation works on an inverse square. So if we go 5 times as far away, what ends up happening is the gravity on the second one is going to be 1/25th when 5 meters apart. Okay. So yeah. Now let's trash that. And let's go back to mouse version. And we'll go. Okay, Andy and Angie go shopping. And are racing to put groceries in the back of their car. In order to do so, they must raise each bag of groceries, which each have a mass of 4 kilograms, a height of 1.5 meters. It takes Andy 2 seconds to do this, and Angie 1.4 seconds to do this. Determine the work and power exerted by both in lifting their bags. Okay, so when we're looking at work, right, we know that work equals force times distance. Now, we're not given a force here, but we are given mass, right, which is important because we know that force equals mass times acceleration. Well, the mass here is 4 kilograms. The acceleration, remember when we're lifting things, the acceleration we have to hit is 9.81 meters per second squared. So the force applied by both of these, 9.81 equals, so the force here is going to be 39.24 newtons. Okay, let me move this out of the way. So we have 39.24 newtons here. Okay, we're lifting each one of them, so that means that our work is going to be 39.24 times distance, 1.5 meters. And so we're going to get 39.24 times 1.5. We're going to get 58.86 joules or newton meters. Either one's fine. Now notice we only have one sig fig here, so we're going to call the work here just 60 joules. Okay, so what we would then do is we would take, we know that power equals work divided by time, so we would figure out Andy's power and Angie's power. right? And so we would just do the work that we just did, divided by each of their time, and that will tell you how much they do. Okay, and it decides to go ice skating over kinetic energy is 1,650 joules while skating at 8 meters per second. What is your kinetic energy at 1,800? Okay, so we know kinetic energy equals 1/2 mv squared, right? So what we can actually do is we can figure out her mass, which is what we need to do, okay? So we go 1650 joules equals 1/2 times m times 8 meters per second squared. We're going to solve that for m, and then we're going to plug that m in to this equation here, which, of course, my pen went for like all of 8 seconds. So we're going to plug it into 1,800 joules. I wonder if I can I can. Oh, that's darkness. I can make you a little bit smaller. 1,800 joules equals 1/2 the mass that we just found times v squared. And that v squared right there, that's what we're going to look. So we know that v equals 2ke over mass. We're going to square root that because it's squared. So we'll already know, we know that kinetic energy is 1,800 joules. We'll have found the mass in the first part of the problem, and that'll give us our velocity. Okay? So that's how you solve that one. Nope. Go back up here. Okay, box has finally run away. Probably sick and tired of being in the middle of all these problems that Andy and Angie have. Okay, so unfortunately its sense of direction is fairly shoddy. It's stuck running in a wide circle. If it weighs 130 newtons and is traveling at 32 kilometers an hour, what centripetal force is acting upon it as it goes around a curve with a diameter of 2.4 kilometers? Okay, so this is just a mean problem altogether. And here's why. Because when we look at centripetal force, we know that centripetal force is in newtons. Newtons, remember, is kilogram meters per second squared. Okay? So what we're going to need to do is turn everything into kilogram meters and second squared. So half of this problem really is doing your unit conversions. So let's start off with mass. So because, guys, the centripetal force equals mass times tangential velocity squared over radius squared. Okay? That's the equation. So, no, it's not. It's just radius. I was getting my centripetal force and my tangent and my gravitational equations mixed up. It's just m times v sub t squared over r. Okay? And that's going to give me kilograms per meter squared, which is newtons. Okay. First things first. We first need to figure out mass. Okay? We know force equals mass times acceleration, Newton's second law. So mass equals force divided by acceleration, or in this case, 130 divided by 9.81. We're traveling at 32 kilometers an hour. We know that to go from kilometers per hour to meters per second, hey, look at this. We just divide by 3.2, which is super easy. And then finally, we have a diameter of 2.4 kilometers. So the first thing we want to do is we want to go 2.4 kilometers. We want to divide by 2 pi. Be really careful on your calculators when you do this. How I would suggest doing it is going 2.4 divide by 2 divide by pi. Okay? And and that's going to give you your answer, right? And that's going to be the radius, okay? But that's the radius in kilometers. So what we need to do then is multiply that by 1,000 to get the radius in meters. Okay, so now you're going to have your mass, your velocity, and your radius. Plug them all into this bad boy, and that is how you solve that equation. That'll give you your centripetal force. Let's dump that. So feel free to pause this. One of the reasons I'm not actually giving you this is because I want you guys to actually work through these problems. And in the past, what's happened is people have just kind of copied the answers. I know all of you guys are sitting there watching this going, who, me? Who would dare just sit there and look at this and copy down and not actually trying to learn what to do? Because you're more worried about the 10 points on an assignment than you would be about the, actual final grade. So, next up, Angie and Andy have decided to play bumper cars with Zambonis. Zambonis are those big things people use to clear the ice of the hockey games, in case you're wondering. Angie's Zamboni has a mass of 1,300 kilograms, while Andy's has a mass of 1,800 kilograms. Angie's is traveling at 12 meters to the east, meters per second to the east. Andy's is traveling at 8.0 meters to the west. They collide, stick together, and slide to a stop over the course of 12.0 meters. Determining the following. This is a lot. The velocity of the Zambonis directly after the collision, the loss of kinetic energy following the collision, and the coefficient of kinetic friction between the ice and the Zamboni. So this is a lot, but you know what? We got this. So let's just jump into it, okay? It'd be wonderful if my pen worked. Cool. It's going to work for like 8.5 seconds. So first things first, velocity. So they stick together. So we know that this is a inelastic collision. If you're not sure how to put that together, go back to the beginning of this video and we talk about it. So we know mass A equals 1,300 kilograms. And V sub A sub I is going, I'm going to use east as positive and west as negative because that's just how I roll. I'm sorry you all had to hear that. I promise never to say how I roll ever again. V sub B sub I equals 8 meters per second. Now notice that I'm putting in 12 and 8. I'm not actually doing all of the sig figs right now, but each one of these numbers. So the mass has 4 sig figs. The velocity does have 3 sig figs. So our answer is going to have 3 sig figs. Also, the distance here is 3 sig figs. So what we're going to do is we're going to go 1,300 times 12 plus 1,800 times 8 equals 1,300 plus 1,800 times V sub F. Okay, and that's a negative 8. So we're just going to put those together. We're going to do that math, and we're going to figure out what the velocity of the Zamboni is. Now, keep in mind, the velocity needs to be directional, right? So if this is a test, I'll probably have the same meters per second, and then give you both an east and a west option in it. So make sure that you're keeping track of your positives and your negatives, because this is a vector measurement, so it's got to have both a direction and a magnitude. So that direction is really important. Loss of kinetic energy. Okay, remember that our loss of kinetic energy equals our final kinetic energy minus our initial kinetic energy. Okay, so what that's going to look like is we're going to take that final. So kinetic energy is 1/2 mv squared. So our final kinetic energy, oh, and there it goes. It was a little longer than 8.5 seconds, but we're going to take our final kinetic energy, which is 1/2. Our mass is the sum of those two. So that's 3,100 kilograms. And we're going to multiply that by our final velocity squared. We're then going to subtract from that both of our initial kinetic energies, right? So we go 1/2 1,300 times 12 squared and we're going to add to that number 1/2 1800 times 8 squared. So we add both of our initial kinetic energies together and then subtract it from our final. Just to keep everything straight, I would advise doing this part separately. So put all of your info into the calculator, figure out the final kinetic energy. Then instead of trying to do it all at once, because you can get screwed up with the positives, negatives, and give you a really different answer than the right one, you could do 1/2 times 1300 times 12 squared plus 1/2 1800 times 8 squared. So just so you guys know, for 1/2, I just do 0.5. So if I was doing 0.5 times 1800 times 8 squared, I would literally just put that in my calculator. 0.5 times 1800 times, and I know that 8 squared is 64, so I'm just going to plug that in, and I get 57,600 joules. Okay, so that's just the kinetic energy of Andy's Zamboni, right? Now I would add to that the kinetic energy of Angie's Zamboni, and subtract, so that would be your initial kinetic energy is the sum of those two together. Okay. So make sure you're working through this. I would then subtract the, we would then subtract that from that 1/2 3100 times 18. Okay, so now what I'm going to do, let me dump all this. And okay, there we go. Sorry. Let me go back here. And then, so let's take a look at that last part, that coefficient of kinetic friction. So here's the thing. Coefficient of kinetic friction equals the force of kinetic friction over normal force. Okay. So I'm going to set this up like this. Over here, we're going to find the force of kinetic friction. Over here, we're going to find normal force. Normal force, super easy. Because we're not on a ramp, we know that the normal force is just going to be mass times gravity, right? Remember, normal force is that force of the ground or a table or anything supporting another object that stops it from going through here. So we know our mass is 3,100 kilograms, and acceleration due to gravity is 9.81 meters per second squared. Okay, so that's going to be our normal force, whatever number that is. It looks to be probably in the range of 30,000 newtons, which makes sense because you're going to have 2 Zambonis. It's a big number. Force of kinetic friction, okay? So the force of kinetic friction, we're going to do this a little bit differently. Because remember that, so we're going to do this through work, okay? We're going to look at the work that friction does. So friction, we know that work equals the change in kinetic energy. We know that it comes to a stop over 12 meters, right? So we know the change in kinetic energy is going to be negative whatever our final kinetic energy was, right? So after they have a crash together, they're going to have a certain amount of kinetic energy. That's 1/2 3,100 times v sub f squared. We had to figure that out for the last part. We then lose that over, what's it called? We then lose that over 12 meters, okay? So now we have work equals negative KE. Now, okay, so this gets a little weird, but this is what, okay, so we know delta KE in general equals final minus initial. But we're breaking the problem into 2 parts, right? We have pre-collision and then we have post-collision, okay? Here, whatever the final kinetic energy is at the time of the collision is going to be the initial kinetic energy for slowing down. I know that's a little confusing, but hopefully that makes sense. When we're talking about the final kinetic energy in terms of the collision, we're talking about how much kinetic energy the two Zambonis had directly after the collision. Friction then brings them to a stop in 12 meters. So then that what we just computed as the final kinetic energy now becomes our initial kinetic energy for the purposes of our friction problem. Okay, so we have negative kinetic energy there. We also know that work equals force times distance. So we have our negative kinetic energy initial there. And we know that the distance is 12, so we're going to divide by 18. So the force applied now is going to be this. It's going to be how much kinetic energy was lost divided by 12. And that's going to be our force of kinetic friction. Our normal force is going to be the mass times 9.81. We divide the two, we get our coefficient of kinetic friction. Know how to do that. Practice that. Okay? This is now the third time, or this is the second time you've had to do that. The third time might be on the final. So, and that's it. So those are all the things that you had to do for the final review. There are a lot of different parts in here that require you to use a lot of different skills. You're not going to have, there might be 2 or 3 problems this complicated on the final. So let me show you how the final's kind of going to be built. I think there are 26 questions total. Let me get them right. Okay. So there are 26 questions total. I believe out of those, and this is just if I'm remembering right, 10 of those are going to be 3-point questions. Okay. Those are going to be super straightforward. They're going to be questions like, a force of 12 newtons acts on a mass of 2 kilograms. What's the acceleration? Right? And so we go 12 divided by 2 gives me, that's a question mark, not a 2. 12 divided by 2 gives me 6 meters per second squared. Cool. Okay. So that's a 3-point question. You're going to get 2 points for work shown, 1 point for the answer. Now, for a question like that, I do want to see Fa equals F over m. So acceleration equals 12 newtons over 2 kilograms. So acceleration equals 6.0 or 6, just because we only have 1 sig fig, meter per second squared. Okay, that's what I would expect to see. Okay, 2 points in the final. You can write out all your work. Don't get lazy. Last big test here. Okay, so we have 10 questions like that. There were 3 points each, so that is 30 points. We are then going to have, I'm going to go 3 5-point questions. Sorry, there are actually 5 because one of the questions has multiple parts. Okay, so these 5-point questions, they're going to need to show the work, right? I'm going to need to see the equations. I'm going to see you know what you're doing. Don't skimp on this, okay? So that is 25 points. Okay. Now, if you're doing the math at home, you'll realize that leaves 11 points separate left, okay, or 11 questions left. Those are questions like, those are CFA type questions. Those are questions like, actually, I'm going to go 6 here. I'm going to take one of those away. This becomes 27. This becomes 30. I just realized one of the problems, I'm actually going to make it a 5-point problem, not a 3-point problem. So that's still, but that still leaves us with 11 questions left. Actually, it doesn't. It leaves us with, because I forgot one of those is 1, 2. Only 3 questions here, but there's 6. One has 3 parts, right? So we talked about that. So that's 9, 10, 11, 12. So that means I think 14. It's either 13 or 14, like that. So let's call it 14 for right now. So that's 14 points right there. Okay. So we add all those up, 3, 4, 5, 6, 71. So I told you it was about 70 points, and that is exactly what ends up happening. So it's 71 points. Notice where all those points are, right? Of those points, 26 are for right or wrong. So 71 minus 26 gives us 45. So 45, this is right or wrong. So if you turn in a perfect final with 0 work shown, you will get a 26 out of 71. Okay, and that is a 37%. The remainder of your points, the other 63%. Okay, so this is 63% of your final grade. Or times 0.2, if we wanted to be super. This is 13% roughly of your total grade in physics. It's going to be your work shown on your final. Okay? So don't skimp out. Don't think that you can, I'll do fine. Like, you guys know better. You guys know that I'm not messing around, that you need to show your work. I care. I was talking to someone in class today, and I said this, and I'll repeat that here. The reason that I care so much about work shown is someone said, well, I'm not sure if I'm going to get the right answer, so why even try? And I'm like, okay, that's fair. However, here's the thing. I care about that you guys know how to do the process, right? I don't particularly care on the final whether or not you get the right answer. That's why only like 37% of your grade is the right answer. What I care about is your ability to replicate the process that is most likely to give you the right answer. And so I gave this example. I make sourdough bread at home, have for over 10 years, okay? And I follow the same process every single time. And I would say that about 80% of the time, 80, 90% of the time, it comes out wonderful. The other 10 to 20% of the time, it just, I don't know. Something happens. I don't know what happened. Maybe it just didn't rise right. Like, it's good, but it's not great. But I keep doing the exact same thing because this is the process that I use that's going to give me the best chance to get that great loaf of bread. And so what I want you guys to do is I want you guys to be in that position to give yourself the best chance to get the right answer. So that's why I care so much about the work shown, was because I care to see what you guys learned, not whether you can guess well on a final or whether you manage to cheat on a final or whether somehow you just, pulled that number out of your tush. I care about how you got it. And that's why 63% of your final is going to be work shown. So again, you don't turn in if you just sit there and go, yeah, I just guessed, I don't have a work shown page, the highest score you can get is going to be a 26. Okay? Which is not good. And that's, again, if you manage to somehow get every question right on the final without showing any work, which, FYI, has never happened. So that's the end of this video. Just so you guys know, I'm also going to be publishing another video on YouTube that is a walkthrough of the last test we took. It goes over some of the common problems that people had, some of the common mistakes they had, and going into the final, I think it's worth a watch. So, yeah, I'll probably put a link to it or something in the Google Classroom. Anyway, happy studying. And stop. Oh, I'm still in draw mode, so I need to go back here. Now